Let's find out whether the series converges or diverges. This one is actually a bit difficult. You can try the ratio test, the integral test, the comparison test, whatever you want to, but you will not get an answer until you do the limit comparison test, and we're required to use the limit comparison test to compare it to 1 over n, which of course we know is a harmonic series. And the limit comparison test basically says take the limit as n approaches infinity of this function, sine of 1 over n, divided by the function that we're comparing this to, which is 1 over n. And just so that this isn't confusing, you can also write sine 1 over n over 1 over 1 over n. And this, there is no way to find this out apart from just going on. Do not expand, or do not multiply outers and inners. You have to use L'Hopital here. And from that we get that the limit as n approaches infinity is, so what's the derivative of the numerator? It's going to be cosine of 1 over n times the derivative of 1 over n. You don't even have to bother finding what this is. Obviously, it's not utterly difficult to find it, but you can just leave it as this, because what you have downstairs in the denominator is 1 over n. And by L'Hopital, we have to find the derivative of the denominator as well. If you don't know L'Hopital, then watch my videos on L'Hopital. And so the derivative of the denominator is essentially this. This is derivative of the denominator. And look at this. You can nicely cancel these out. And from that, you get that this all of this is equal to, and I have to squeeze it here again, the limit as n approaches infinity of cosine of 1 over n. And if you plug in infinity into n, then you get cosine of 0. And of course we know that cosine of 0 is equal to 1. Therefore, you can conclude that since this sequence diverges, and we know that it diverges because it is a harmonic series, not sequence, sorry, series, then we can also say that by comparison test, by limit comparison test, the given series converges as well, because if you get a finite and positive number as your answer to the limit as n approaches infinity of the original function divided by the function you're comparing the original function to, then a finite and positive answer will tell you that if one is divergent, then the other one is divergent. Similarly, if one is convergent, then the other is convergent as well. But because the harmonic series is divergent, you can just conclude that this is divergent by limit comparison test. And that is your answer.